This is about circuit protection. I did a thing about circuit protection a time ago, and that was bad enough. But circuit protection becomes harder, becomes different when you get circuits that are interconnected with each other. So I'm going to do a trivial case to show how much of a circuit is protection. When you design a circuit, how much of the circuit design is protection circuit. And then I'll go on to H-bridge. Now the H-bridge part is how or why DC controllers occasionally fail, and why DCC decoders oftentimes fail. And then I've got a couple of things about I squared C. Not everybody understands I squared C as well as they think they do, and hopefully I'm going to explain that to you. And then there's another problem with servos that's related to this, and I'm going to cut through that as well. So if I start with the single-ended design, and I've put in red, never, ever, ever use this circuit under any circumstances for anything, because it will burn something on you. If you connect a microchip to a motor like that, then what will happen is when the microchip goes high, power comes out in that output pin, the motor will burn out. An electric motor inside is a couple of bits of metal, one of which is magnetic, and a coil of wire. Now, a coil of wire has got a low resistance, so lots of current, and it's got a high inductance. Low resistance is enough to blow the chip, but even if it doesn't, then when the motor commutates, when it tries to change from one state to another, the inductance will try to keep the current flowing. And in order to do that, it'll put a reverse voltage back out, and that'll blow the chip. Always remember that an inductor is trying to keep things from changing. Your typical microchip, an Arduino or a PIC or whatever, looks something like this. And if you look carefully at that, the first thing you notice are the bond wires. Those are much finer than a human hair. They're finer than one of David's optical fibres. 5 milliamps per pin is typical. 25 milliamps for the whole chip is typical as well. If you think about it, if I've got 5 milliamps going out on an I/O pin, then that 5 milliamps has also got to go in via the power pin. And if I've got more than one I/O pin putting out current, then all of that current has to go in through the power pins. And so you get those faults happening whereby the bond wires, as they're called, fuse. And the thing that happens quite often, Davey gets it and I've had it quite a bit, where somebody says they've got a chip and it's not working, but the chip's not blown up dead, black smoke coming out of it, anything like that. It's simply one of the pins has stopped going up and down. And very often the reason that the pin has stopped going up and down is because the bond wire has fused. And if not the bond wire, then the little square, which is the output transistor that the bond wire's connected to, has fused. So going back to that single-ended circuit, this is how you would actually work a single-ended circuit. The transistor Q1 is there to protect the microchip from having to put out too much current. The transistor will multiply the current that goes in on the base, the B connection there, by 180, 200 maybe. So if I put a milliamp into the base, which is much less than is dangerous to the chip, so 1 milliamp into the base will give me 200 milliamps through the collector, which is marked C, and therefore through the motor, and that'll make the motor work. So far, so good. However, if the transistor's switched on, then between B and E of the transistor, there's only about 0.7 of a volt. So if I've got 5 volts coming out of the microchip and 0.7 of a volt at the base of the transistor, then there's 4.3, 4.4 volts somewhere that has to be found a place for. And so what happens is we put that resistor, RBS, in there. And RBS will be 5 volts minus 0.6 of a volt is 4.4 volts at 1 milliamp. 4.4 volts at 1 milliamp is 4.4 kilo ohms. So I'll use a 4.7 kilo ohm or a 3.9k. And then lastly, when I switch, the microchip switches the transistor off or on. Remember, the inductance of the motor is going to try and keep the current flowing. So for that reason, I've added a diode across the motor. And that diode, it's called a flywheel diode, sometimes called a snubber. And sometimes instead of a diode, it's a capacitor or a capacitor resistor network. But what its job is to do is to let current from the motor escape round about without going anywhere near the transistor Q1. So in that circuit, we've got a microchip and we've got a motor, but Q1's there to protect the chip, RBS is there to protect the chip, and D1 is there to protect Q1. In reality, if we were using this for a proper railway modelling application, then we'd use PWM coming out of the microchip to alter the speed of the motor. And we'd also then need to add a changeover switch to alter the direction of the motor so that the motor can go in both directions, be it for a traction motor on a loco or for some animation or other. The way this is very often done in industry, in reality, in the big world, is to use a thing called an H-bridge. And it's called an H-bridge because of the shape of it. If you can see the two lines down the left and right of the motor and the bar across that goes through the motor makes the shape of an H. Now, in order to simplify the wiring, I have excluded most of it. The output for the microchip on pin A goes to the inputs to the transistors on A on both sides. And the Bs, all three Bs, are connected. So output A of the microchip turns the top left transistor and the bottom right transistor on and off. And output B of the microchip turns the bottom left and top right transistors on and off. Now, we've already done quite a bit on the H-bridge. David Dick did a presentation on this a number of years ago, and I've just put a QR code up, and if you follow that QR code, it'll take you to Davy's presentation on using the L293. The L293 is a single chip solution for an H-bridge. It's got the whole of the H-bridge built into a 14 pin or a 18 pin chip, and all you have to do is wire it to your microchip. Now, looking at that chip, that arrangement there, the 4 transistors are effectively switches. So if I put in a 1 out on output A of the microchip, then the top left switch gets closed and the bottom right switch gets closed. So because those 2 transistors are on. So current can flow down through the top left transistor, left to right through the motor, which makes the motor turn clockwise, and then flow from the motor down through the other transistor to ground. And so the motor rotates. There's no general rule that left to right through the motor makes the motor go clockwise. It depends what end of the motor you're looking at. So I've just arbitrarily said, right, I'm going to do that left to right through the motor makes it go clockwise. Similarly, in the same way, when there's a 1 coming out of option B on the microchip, the B switches are closed. The bottom left one's on and the upper right one's on. So current can now flow down through the upper right, right to left through the motor, and down through the bottom left transistor. And because the current's going through the motor the opposite way, the motor will rotate in the opposite direction. So this time the motor goes counterclockwise. This way, my DC controller or my DCC decoder can make the motor move in either direction. The most common use for a motor like this with an H-bridge is traction, because this is for heavy current, for high power, for doing quite a bit of work. And what you'd do there is you would put PWM, pulse width modulated signals, onto A and B. And if the duty cycle is 50%, then the motions will cancel out and the motor will stay still. And using your control knob, you can either go from turning it anti-clockwise to make the motor spin anti-clockwise, to turning it clockwise to make the motor go clockwise. However, what happens if at some time all four of those switches get clicked shut at the same time? And at that point, all four transistors are closed, because I've got two ones on the microchip. Now this could have happened because of sloppy programming. It could have happened because my microchip's got its bits in a twist and it's made a mistake. There could happen because of capacitive delays, inductive delays. There's a half a dozen reasons why that microchip might put out two ones. If it does put out two ones, all four transistors on the H bridge are now closed. So all four transistors pass current. At this point, we've got a short circuit across the supply. So either the supply will fuse, the printed circuit board tracks will fuse, or some of these transistors will fuse. Either road up, magic smoke will escape, and it's a bad thing. So we have to be very careful with our H bridge that this area here, where signal A is going down, doesn't coincide with where signal B is going up. Or similarly, when signal B is going down, it can't coincide when signal A is going up. Now this is what's called shoot through, and it's a lot of energy gets put into stopping, limiting shoot through. If it's a dead short like that, shoot through happens and you have a pop. Much more insidious though is cut through, whereby you have a short. Now let me just explain that diagram there is not to scale. The transition where the signals are going up and down might only be a few nanoseconds, but the length when it is up and is down might be many, many milliseconds. But rather than put a great big long diagram, I've expanded the dangerous part. So if they're both on at the same time, but it's only for a nanosecond every millisecond, then that's not long enough to pop anything. But what it is long enough to wear things. This power supply is finding that it's having to supply more current than it's designed for. The tracks are suddenly taking more current than they were designed for. The transistors they're almost certainly hurting, and they might not die immediately. It's not a case of, oh, this, you switch it on and pop, there's been a mistake made, we're going to have to fix this. This, you could switch it on and it could run for months before it dies. And then you replace it with an identical one and it runs for months before it dies because of cut through. Cut through is much more insidious than shoot through on a bridge, but it's something you have to think about. They're both caused by the overlapping of the A and B phases of the motor control signals in the H bridge. They're both caused by low duty cycles. There's a big danger when starting up and shutting down. If you think about it, the power supply comes up, the transistors might be switched on, might be switched off, there might be capacitors that are charged, The outputs of the chip might not start at the same time. You have to wait for the chip waking up and operating its outputs and getting them into the right state. Start up and shutdown is a great time for shoot through and cut through to happen. Delays because of capacitors, delays because of semiconductors have got internal capacitors, and that causes the semiconductors to only rise and fall slowly. And or mistakes or errors in the firmware or delays in the firmware can also cause these things to happen. It can cause a short circuit to your power supply in the worst case. It can cause overcurrent in the transistors. It can cause overcurrent in the power supply without shorting it. It can just make it be partially driving too high a current without actually popping anything. Track, by track I mean printed circuit board track, not rail track. PCB tracks are designed to take a current and no more than that. And this is a good way of blowing currents on a PCB. Fuses, heat, and as I say, it might be subtle, it might shorten the life of things without actually making them go pop. So there's a number of ways to try and design past it. First of all, deadband. Again here, deadband, I've stretched the diagram to make it very obvious what I'm talking about. But what I've done here is designed in each of the pulses has got a front porch before it goes high and a back porch after it goes low before the other one goes into its front porch and then goes high. This means there's always an area called the dead band, and there's the dead band there. And if you've got a good H-bridge controller, it will have dead band settings in it. And the best way to make sure you have dead band is not to control the H-bridge yourself. A lot of people take an H-bridge, make an H-bridge out of 4 transistors, and then they use a 555 or something to drive it. So that when the output of the 555 goes high to one transistor, it goes low to another. That's liable to give you a no deadband situation. The better way to do it is to use a CWG, a complementary waveform generator in firmware. Now, here's the data sheet for a 16F 18313. This is a 8-pin pick, very, very popular at the minute. A lot of people are using it. For example, the guys in the JAL special interest group are currently using this chip to replace all the 12F675s in the pocket money kits. And the reason they're doing that is this chip is cheaper and easy to get your hands on and more affordable than the old 12F675s. It's an 8-pin chip, but it's got lots of peripherals on it that the old 675 doesn't have. It's got an analog to digital converter. Now, an ADC is a very complicated animal. And this ADC is a very complicated ADC. It's got averaging and negative resistance selectors. It's got a temperature sensor built in. It's got a lot of good stuff going on. But in the data sheet, the ADC has got 14 pages of how to use it. The same data sheet has got 22 pages on how to use the complementary waveform generator to make sure you don't get deadband if you use this chip to drive a motor, because a lot of people in industry put a lot of effort into driving complementary waveforms to drive H-bridges. The CWG on this chip has got 6 different modes. It's got dozens of options. It's a non-trivial thing. It takes a lot of time to get it right, but it guarantees that you'll always have deadband. And the deadband might only be in nanoseconds. But if you think about it, if you've got a motor that's kicking back and sending a pulse of current back, that might be enough that you need deadband in milliseconds. And so you have to accommodate that. Other things you can do is you can use a weak pull-up on your microchip. if it's available. They don't always have them, but I can make an RC circuit that stops deadband happening if you're getting capacitive problems with these things. Stiffen your board wiring, either make the tracks bigger, or a common trick is to a track that's there and is passing current. To make it pass more current, you simply put a piece of solid wire over it and solder the solid wire to it. And that makes that track stiffer, makes that track capable of passing more current. Your transistors, heat sinking them or improving the heat sink on them, riveting them to a heat sink, something like that, will mean that if you do have cut through, the transistors last longer before they die. And always worst case testing, that's just a design thing. You make sure that you work out what's the worst possible thing that could happen. Now at this point, I could talk about pull-ups, but I'm not going to. I've got some extra, there's another half dozen slides in this presentation about what pull-up resistors are and where we use them, but I'm going to cut straight through to something else because it's already long enough and I'm already boring you enough. So I'm going to go straight through and talk about the fallacy that people have on I squared C. And the fallacy that people have about I squared C isn't the fallacy that you think people have about I squared C. There's a typical I squared C setup. You've got a master device and you've got a number of devices. They're not allowed to be called slaves anymore. So it's a master device and it's devices. Now these devices and master devices may share a power supply, the plus 5 volts or the plus 3.3 volts, but they don't have to. If you're using EasyBus or Megapoints, those are I squared C based devices and you don't always have to have the same supply. You can have local regulators on your output devices or your input devices that mean that you have a different supply on those. It may include level shifters, but I'm not including them in this discussion because it's just a complication that we don't need. RP over to the right of that diagram are the pull-up resistors, and those should be 4.7k or 10k pull-up resistors. And the first fallacy that people say is those are for termination reasons. That's to stop signals bouncing along the bus. And that's not true. They're pull-up resistors for a reason that I'll explain in a minute. And the second fallacy that people say is that you can do without those resistors. It'll work just fine without them. It won't. And that's for a reason that I'm about to explain. If I look at the waveforms on I squared C, there's two wires, SCL and SDA. That's the serial clock and the serial data. And there's what happens. Now, you don't have to understand, you don't have to even be interested in addresses or datas or acknowledgements or any of that stuff. I only need you to look over at the extreme left-hand side of that diagram. Inside the dotted box, you'll see that SDA and SCL are both high. They're set to 1. And any device can pull the SDA line down to 0. And that is the start of a transfer. If the SDA line goes to 0, then the master device starts putting out clock pulses. And those clock pulses initiate the transfer and acknowledgements and all that happy bananas. But the only thing I'm interested in is that the bus is sitting with 2 1s on it until something pulls the SDA line down to 0. And that all seems very reasonable, except for this. Let's say the master pulls the SDA line down to 0. Then the 0 volts of the master chip is now connected to the SDA line. But all the other devices are at 1. And so their SDA lines are currently connected to the 5 volts line. So I've now got a dead short from 0 volts down through that chip, the master chip, to the SDA line, to all of the devices, and up through their SDA lines to 1. So that's going to cause, at the very least, overcurrent, and much more likely the magic smoke to escape. So to find out the answer to this, I recommend you go and look at that. That incredibly good looking fella there, with a slightly dodgy haircut, did a thing on Charlieplexing. And Charlieplexing is using a microcontroller to switch LEDs on and off so that you can control more LEDs with fewer pins. And one of the tricks there is that if you make the output of a microcontroller into an input, then it effectively open circuits the output of the microcontroller. Because I've made it an input, I've broken the circuit from that microcontroller to those LEDs. I've put the Charlieplexing, a URL and a QR code, so you can go and find the Charlieplexing one if you want to revisit that. But that is what we're going to do here. If, instead of being 1, the SDA and SCL lines, instead of being set to 1, are set to being inputs, then that has a couple of effects. One, those pull-up resistors will pull the wires high. And because those resistors pull SCL and SDA high, every device on the bus will detect that it's gone high. And if I push it low, then what happens is I get a low from the master, but there's no highs on the bus. Everything else is disconnected. But everybody else can read it. So everybody can see what's going on, but nobody has got a 1 going out, so nobody's passing current. So what I do is my I2C device, any device, has got 2 states, but they're not 1 and 0. Everybody thinks, this is the fallacy, everybody thinks that in I2C you have a 1 and a 0 on the buses. You don't. You have a 0 and you have a high impedance state, and the high impedance state gets pulled up by those resistors and all the chips notice it. And if you actually go into the libraries, this is the twi.cpp. This is the library for Arduino for doing I2C. And the code in it is essentially this. Make both SDA and SCL, I have simplified this enormously to put it up here. Make both the bus lines outputs and put a 0 on them, and then make them inputs. And that's it. And then in the main loop, if this bit is to be low, then what you do is you put it to an output. And putting it to an output, because it's already set to 0, putting it to an output sends a 0 to the bus. But if you want to send a 1 to the bus, then what you do is you set the pin to be an input. And because you've set the pin to be an input, the resistor, the pull-up resistor, will let the bus pull up to a 1. And so if you're writing code for this, this is the way you should do it. You should never send a 1 to the bus. And if you do send 1s to the bus, then you're liable to cause a short circuit. You're liable to cause either strike through, shoot through, or cut through, which means you're liable to damage something. Now there's a servo. I just got that servo from China. a pound. And the servo, like the I squared C, is disparate devices talking to each other. That servo, I've got no idea what's in it. I mean, you're paying a pound from it from China. It could be anything that's inside it. If you know about how servo mechanisms work, the input there could be an op amp. And if it's an op amp, it's got a virtual ground in the input. It could be a differentiator or an integrator with an op amp circuit, in which case you've got a discharged capacitor that you're having to worry about. It could be an input pin to a microcontroller. It could be a DAC pin to a microcontroller. It could be an ADC pin on a microcontroller. It could be a standalone ADC. It could be a standalone DAC. I have got no idea what clever circuitry my little Chinese buddy has put on the input pin of that servo. And I've got no idea how it's going to behave, particularly when I first switch it on. When I first put electricity into that circuit, it could be that I get a 1 in the microchip and I get a 0 in the servo, or it could be that I get a 1 on the servo and a 0 in the microchip. Either way, I could damage either the microchip or the servo, and I don't know which one. If I put a pull-up resistor on the servo, on its signal, then it doesn't matter who puts ones or zeros on. That pull-up resistor will mean that any zeros will cause the supply voltage to appear across the pull-up resistor and not go to either the microchip or the servo. I had a look. On my machine, I just opened it up, the library manager for Arduino, and said, for all libraries, how many have got servo in them? How many are there for servos? And I found 135 servo libraries. And I looked through half a dozen of them. And after looking through half a dozen of them, I was losing the will to live. Some of them use the right thing whereby you make the output pin an input if you want it to go high. Others were just putting ones and zeros out and giving the reason, giving an excuse for this cut through thing to happen. You are left with a number of choices here. Some of I have to say, in their defence, not all the authors of these libraries are hardware aware. A lot of these people are computer people and microcomputer people, and they know that to make a servo work, you put it to 1 and you put it to 0, and they're not thinking about current and stuff like that, and current flowing backwards and all that sort of stuff. They just know that they want ones and zeros. So some of them have the excuse that they're not hardware aware, but at the same time, it's not good. You get a number of options here. You can just pick your servo library, connect your servo and hope for the best. You can pick your library and go into it and see if you can fix it, and then save that library under a different name and make sure you use that library with that servo and all that good stuff. You can go into the hardware and see what's going on, get the oscilloscope out, or you could just bang a pull-up on it. If you just bang a pull-up on it, then if it needs a pull-up and you've put one on it, you're golden. If it needed a pull-up but you don't put one on it, then you're looking at trouble. If it didn't need a pull-up and you didn't put one on, that doesn't matter, you're still golden. If it doesn't need a pull-up and you put one on, then you're still golden. It won't do anything adding an extra 1 milliamp, an extra 4.7k won't hurt anything, but it might save the servo or it might save the pin on your microchip. And as for how to do it, it's very, very simple. There's a servo connector. This is in Lochmaster. There's the 3 pins that go to the servo. I always remember the 3 pins that go to the servo because in order they're GPS G for ground, which is the black wire, P for power, which is the red wire, and then S for the signal, which is the orange or brown wire. But GPS is very easy to remember. And having showed you how to do it in Lockmaster, it's only fair that I show you how to do it in reality. And there it is, a 3-pin connector to go to the servo, and a 4.7 kilo ohm resistor across those two pins for safety's sake. £5 will buy you 500 4.7k resistors that are that size. Those are, if I just go to the previous module, that resistor is a what's called a 1206 resistor. It's a nice, big, easy to use SMD resistor, and it goes beautifully across two lines of airboard. You can buy, as I say, 500 of them for a fiver. Anyway, to finish up, you must be very, very wary if you have independent systems that are connected to each other. It looks dead simple. You plug the output of that one into the input of that one, but it ain't always as simple as that. You should always share your 0 volt reference. I didn't emphasise the getting the 0 volts part of this right very much today, because I've went on about this the last 2 or 3 of these that I've done. Always get the grounds together, get them right. And then always think about how could these modules destroy each other if I gave them a chance. Always think about banging in a safety pull-up. 3K3, 3K9, 4K7 are the typical values, 10K at a push. If something dies after a few weeks or months, and then you replace it, and the new one dies after a few weeks or months, that could be cut through. That could be that there's a couple of signals that are passing each other a wee bit tight, a wee bit close to spec, and you need to look at either decoupling them or adding a pull-up. And if you're coding, use this trick of always push a 0 out, assert a low by putting a 0 on it as the output, but make it an input and let it float high, and that way you'll never cause a short circuit. And if you're coding also, and you're going in, mucking about with the chips, putting the settings on a microchip, you should know about weak pull-ups, or you should maybe be thinking about using external pull-ups on your design. Electronics designers should be doing this. They should be always designing for safety. Implementers, that's us, should always assume that the designers missed this, and so we should always have a wee eye on how to do things safely. Primary concern is always make sure nobody gets hurt, but secondary concern is make sure nothing gets damaged, either immediately when you switch it on, or 3 weeks down the line from now when it's had time to wear out, because it costs to repair and replace things. There's downtime while you're getting replacements because you burnt the one out, and it's deeply inconvenient if you have to get underneath the board and your soldering iron drops solder on you, and that's the whole other conversation, and we've already had that. So I've done all the damage I can do. I'm going to throw it open to the floor for any questions or comments.